In this video I'm going to be talking about the Gauss-Seidel method. Okay, so the Gauss-Seidel method is another indirect method for solving systems of linear equations. Okay, so let's say we have our standard form for our linear system of linear equations. Ax equals b. A is a coefficient matrix, x is our vector of unknowns for which we're trying to solve, and b is a constant vector. So what we're going to do is we're going to write A as the sum of three vectors L, D and U. Okay, so this is similar to the Jacobi method. Okay, so L is our lower triangular elements of A, D are the main diagonal elements of A, and U are the upper triangular elements of A. And if I expand out this bracket, so I'm going to be doing a bit of algebraic manipulation. Okay, and we're going to put the all terms not involving dx over to the right hand side. Okay, and if I want to solve for x, I simply pre-multiply by the inverse of d. Okay, so here we have our matrix form of our Gauss-Seidel method, and because this is an iterative method, okay, so what we say is k plus 1 in a superscript. This is our new estimate of the solution for x. Okay, now on the right hand side, with the Jacobi method, both of the x's on the right hand side were of the current iteration. Now for the Gauss-Seidel method, this L times x, these only include the lower triangular elements of A. So as we go through our elements of x, we've already calculated these values for the current iteration. So what I'm going to do here is I'm going to use those current values. Okay, so the superscript here is k plus 1. Okay, now for the u times x, u is the upper triangular elements of A, so I've yet to calculate these for the current iteration, so I'm just going to use the current values x. Okay, so this is the main difference, or this is the difference between the Jacobi and Gauss-Seidel method. In essence, we're using information, or we're using our estimates of x as soon as we've calculated them. So if I was to write this out for the ith value of x, so our new estimate for the ith value of x, the inverse elements of a diagonal matrix is just 1 over the diagonal element, so that's going to be 1 over aii. That's going to be multiplied by bi minus, well, the lower triangular element, so I'm going to replace this lx with a sum, so then the sum goes from j equals 1 to I minus 1. Okay, so all of those values of x prior to the xi. So in the current iteration, I've already calculated some values for x, and that's what I'm going to use here. So these are the lower triangular elements multiplied by those values for which we've already calculated for in the current iteration. The minus ux I'm also going to replace with a summation, and this goes from j equals I plus 1 to n, where n is the number of equations. We have the upper triangular elements multiplied by those values of x for which I've yet to calculate in this current iteration. Okay, so this is our Gauss-Seidel method for solving a linear system. So as always, I'm going to go through a worked example. So this is a short worked example. Okay, so this isn't found in the notes, so this is a new example. So we've got a 3 by 3 matrix, so I'm just going to write down the linear system in matrix form. So there's our coefficient matrix. We have our vector of unknowns for which we're solving for, and we have our constant vector on the right hand side. Okay, so the Gauss-Seidel method, for our first value x1, our improved estimate is going to be equal to 1 over the diagonal element in row 1 column 1, so that's 1 over 2. B1, which is 4 minus 1 lot of x2, and I'm yet to calculate x2 in the current iteration, so that's got a superscript k, minus x3, and likewise I've yet to calculate 3 in the current estimate. Okay, so that's our expression for x1. x2 for our improved estimate is 1 over 3. B2, which is 3, minus 1, so that's plus x1. Now, if we calculate x1 here and we move to x2, we've already got a new value for x1, so we might as well use that. And that's going to be minus 2 lots of x3, but we haven't yet calculated x3, so I still use our current value, or the kth value. And for x3, well, we've calculated x1 and 2, so we can use our new values to update our estimate of x3. So B3 is 9 minus x1 using the k plus 1 estimate, and that's going to be plus 2x2, so that's 2 there, using the k plus 1 estimate as well. Okay, so that's our Gauss-Seidel method for solving this system of equations. Okay, so for the first iteration, let's use starting values. Zeros, remember, it doesn't matter what starting values you use. If the scheme is convergent, and we'll talk about convergence in another video, you'll eventually get the same answer. So it's just useful to start with zeros because it cuts down on the amount of work for the first iteration. So our first, I should say this is our 0th guess. Okay, so our first estimate is 1 over 2, 4 minus, well, x2 and x3 are currently 0, so that makes it quite easy. Okay, our second unknown is x2, so I have 1/3, 3 plus x1, which we've just calculated, so that's 3 plus 2, minus 2 times x3, which is still 0. Okay, so that gives us 1.6667, correct to 4 decimal places, and x3 will be 1/4, and remember, because this is the last unknown in our vector, we can use all of our new values. So it's 9 minus 2 plus 2 lots of 1.6667, and that equals 2.5833. Okay, might as well do another iteration. So this is calculating my second iteration. Okay, so same scheme as before. So we have 1/2, 4 minus our our value for x2, which is 1.6667, minus our value for x3, which is 2.5833, and that is equal to minus 0.125. Okay, x2, so again we have 1 over 3, 3 plus x1, so that's going to be a minus, so it could be minus 0.125, minus 2 times x3, which was 2.5833, which comes out as minus 0.7639. And finally, our new value for x3 is 1 over 4, 9 minus x1, but remember that's a minus, so that's a plus 0.125, plus 2 lots of minus 0.7639, because that was our new value for x2, and that comes out of 1.8993. Okay, so if we were to continue our iterations, we get closer and closer to the actual solution of this linear system.